So a normal distribution is the topic that we will look at today. The graphs we'll look at today will have this special curve. So we call a normal distribution the shape of it, we call a bell curve. But the key thing is if it's a normal distribution, and a distribution is the way we can kind of like set up our data like we did yesterday with the histogram, it's supposed to be symmetrical. So a bell curve is like a nice mound or a nice hill that is exactly the same on either side. So it goes up, comes back down. The key thing with that is it should have symmetry. And if it has symmetry, the other part that should be happening then is that our mean and medians are supposed to be equivalent. And they're going to be in the center of our curve. Because the majority of people are supposed to be at the average. Can't make my line straight. Oh, that's not much better. Oh well. So if I gave a true perfect test, the majority of the people are supposed to be at the average of the test. So if the average is an 85%, most of the people should be around that 85%. I should have then a handful of people that are a little above 85%, a handful of people that are below. And then a smaller handful that would be well above 80%, and a very small handful that would be well below. And that's what a perfect test is supposed to look like. So sometimes teachers, if their data is skewed, meaning if there are a lot of low values, they'll find the mean, and then try and like fix it so that the mean then is more like what the average grade should be. So like if you consider an average grade to be an 85%, they would then take their data and like add some bonus points or whatever, but try and take that value and change your grade. So a lot of professors use this to determine what their test scores would be after it's a curved test. So in the middle is where our mean, you will see the mean as the x bar, is located. And then it is supposed to be symmetrical where I have exactly the same information on the left and the right, the exact same number of data on the left, the exact same number of data values on the right. So we're going to look at another set of values. We're going to try and make one more dot plot to see if we can get other information to try and look more symmetrical or look more like this curve. Bless you.
Bless you.
Thank you. So the question at the top says, does the data create a normal distribution? Meaning, is it symmetrical? Does it look like a bell curve? We're going to skip the number of DVDs. And we're going to go down to number 2 that talks about the lifetime of 20 different light bulbs. So the first thing that we need to do, just like creating a histogram, we have to be able to get intervals. The first one with the heights was already pretty much divided for us. This one is not. So if we need to figure out the intervals that we're using, that's also called the class width. Remember, you need your highest and lowest values because we need to find the range. So looking through the data, what's the highest and lowest value in the data, Virginia?
The lowest is 970.
So here's the lowest value of 970. And the highest number is 1044. So in order to find our class width, so that we get intervals to create some separation down below so that we know where to put our values, we have to take the range. So 1044 minus 970. That tells us the spread of the data. So the spread of this data is 74. And then you're supposed to divide it by the number of classes. If they don't tell you how many classes, what's a good number to use? 5, yeah. Caitlin, do you know what 74 divided by 5 is?
Me?
Yeah.
14. Well,
It would be 14 point something, so if we round up, it would give us 15. Good. Nice doing some quick mental math there. So 74 divided by 5 is 14.8 something, 9. And we always round up, so round up to the next whole number, which gives us 15. So we're going to divide our number line down below, or divide this horizontal line down below. We'll make it pretty much like we made the chart here for the height. So my first tick mark is going to start at the lowest number, which is 970. So this tick mark represents 970. And then our class width is 15. So that means every tick mark needs to represent 15 numbers. So what would the upper bound of my first interval be if it starts at 970?
984.
Nice job. 984. So that's my first interval, 970 to 984. We're going to have 5 of them. So we start at 985. And just write it underneath. And Izza, that one would go to?
999.
Nice, 999. So the next one would be 1,000 up to what is it?
1014.
1,014. 1,015 to?
Oh, me.
Yeah, you're doing so well.
1029
1,029 and then 1,030.
to 1044.
1,044. Which happens to also correspond with the last number. The highest number doesn't have to be the last number in your interval, as long as it's in between that last interval. So it doesn't have to be the last value, it has to at least be in between. So our goal then, after we make our dot plot or your X chart, whatever you want to call it, whatever figure object that you want to make here, does it look like a nice bell curve? Does it look like it's symmetrical? So there are 20 numbers up here. X's, dots, O's, whatever you want to make. See if you can get this data then to fall within our intervals. So starting with 1013, I'm going to use an X. You don't have to use an X. Use whatever you want. See if you can plot the information. I tried to be as careful as possible. Anybody get a graph to match? Yes. So looking at the graph, does it look fairly symmetrical? Does it look like it would be a normal distribution? I would say it's pretty darn close. So yes, interval 2 and interval 4 aren't exactly symmetrical, but this one is pretty close to being a normal distribution, meaning it's very close. If I wanted to draw a curve here, it's pretty close to fitting a nice curve. A bell-shaped curve, that's what that's called, or you can use either word. So yes, this looks fairly close to being what we call a normal distribution. So that means this data is nice and evenly distributed. So using your calculator, I'd like you to take the 20 pieces of data here and see if you can find the standard deviation and then the mean. And we're going to try to start applying that information together. So mean is the middle, which my middle should be in between 1,000 and 1,014. So our mean should fall in between those values. Standard deviation is how far spread apart the data is from that middle. And now we're going to talk about what that actually means and how can that relate to statistical data. did you get for the standard deviation?
17.2.
17.2. Everybody okay with 17.2? Yes, no, maybe so. Yes, okay. And then how about the mean, Kate?
1004.15.
So 1004-ish is definitely in between my 1000 and 114, which is our highest interval. So the mean should correlate with that interval. If it doesn't, then you did a calculation wrong or you totally went wrong with where you're placing the x's and the intervals. So the last question is going to start taking us into what we're going to be working with over the next 3 days. And that now is applying the standard deviation and the mean together. So the mean is the middle. The question says what percent of the data falls within 2 standard deviations of the mean. So if I'm at the middle, a standard deviation within the mean can happen to the left, and that same distance can happen to the right. Remember, that's what absolute value says. So you can have the same distance to the left or to the right. That's considered 1 standard deviation. So the same distance you're moving left and right is 1 standard deviation. So our goal is to figure out 2 standard deviations. So we want to know what percent of the data points fall between 2 standard deviations of the mean. In order to answer that question, we have to get bounds, meaning what numbers would my data apply to? So how do you think you could use the standard deviation and the mean to figure out a number that we can use as a comparison to see, do my values fall within this number? So how can we calculate that? So our goal is to find a lower bound, a lower number, and an upper bound or an upper number, an upper numerical value. So how can I get a number that will be lower than the mean? Or higher than the mean? You have the number 5. Aaron?
Subtract the standard deviation from the mean.
Yeah, so if I want a number that would be lower or higher than a central number, you need to either subtract or add a value. So we're starting with the mean because everything's compared to the mean. So our mean is, 1004.15. We're going to subtract the standard deviation of 17.2, but we want 2 standard deviations. So that means I need to take this number and double it to make it 2 standard deviations. And then we're going to do exactly the same thing, but instead of subtracting, we're going to add so that we can have an upper bound as well. So this is going to be like our max and min numbers. How many of my points that we have listed, data values, fall within these max and min values? So does anybody have the lower number? Sarah?
969.75.
And do you happen to also have the upper number?
1038.5.
So now I want you to look up your data. Sorry. 1038.55. So looking at your numbers, count the values that fall between these two. That's what the question is asking. So what percent of the data falls within 2 standard deviations of the mean? Well, these 2 numbers represent 2 standard deviations from the mean. So if you look at your numbers in the chart, way above here, how many of the numbers that are in the chart are in between 969.75, 970-ish, and 1038.55? Caitlin, are you raising your hand? Or you just...
Oh, no.
Okay.
But 19.
So Caitlin says 19 out of 20 numbers, and 19 out of 20 as a percentage is. So if you had a 19 out of 20, what would your percentage be? A 95%. So 95% of our data is 2 standard deviations from the mean. So So if you look down below, there's something called the empirical rule. If I had a perfect test, it should follow the empirical rule. If we had a perfect set of data, it should follow the empirical rule. So like thinking about statistic wise, most information is supposed to fit this pattern. So there are two little diagrams down below, and I'm going to explain these. You will need these two diagrams for your homework tonight. So make sure that you remember when you're doing your homework, you have to look at these two, or you have to quickly have them memorized, which you're not going to have memorized yet. But after you use them enough, you will get them memorized. So it says the area under the curve. If I have a curve, the area under any curve is 100%, because every number is going to have to be under that curve. I'm not going to have a number that's above it. The curve has to contain all of the values. The first question says about 68, or the first bullet, about 68% of the data is supposed to fall within one standard deviation of the mean. So if you look at your little picture below, the mean is in the middle. That's what mean means. It's the middle number. 68% encompasses a portion to the left and a portion to the right, a distance away from the mean. So 68% of my scores should be within one standard deviation of the mean. Another way of looking at it is saying 34% should be lower, 34% should be higher. That's another way of thinking about it. The second bullet, about 95% of the information should be within two standard deviations. That is exactly what we just showed with the previous problem. 95% of our values were two standard deviations from the mean. Again, looking at, you have the little diagram showing two standard deviations with the 95%, or splitting it up separately. 34%, the next bar has 13.5, and then again above it I've got 13.5. And then the last one is 99.7% of the data should be three standard deviations within the mean, essentially all of it. And again, looking at your graph, you have three standard deviations representing 99.7% of your data. Or splitting it up separately, 2.35, 2.35, and then that last little percentage is just the 0.15% that's left over, which is essentially nothing. I had a huge amount of data, we have scores that represent that. So tonight you'll be asked questions about if something is one standard deviation from the mean. Well, that's what this represents here, one standard deviation, the mean plus a standard deviation. Well, that percentage, I'm looking at both of them, would be 34 plus 34%, so 68%. So a lot of it isn't doing work, it's looking at a chart and trying to correlate what that chart is talking about. So if you flip the page, we're going to try and do a final example. I guess we'll do this first one here. So we're going to try and make our own chart based off of data that you're given. And this is talking about lieutenant governor salaries of 43 state lieutenant governors. Their mean salary is $57,000. And it says their standard deviation is $22,000. So we're going to make ourselves a bell curve. Trying to get a straight line here. Stepping on my thing. So part of your homework will be designing or creating your own bell curve and the numbers that go with it. The mean needs to be in the middle. So in the middle of my bell curve is 57,000. So that's the middle of the curve. It says the standard deviation is 22,000. So I want to label where all of these data values are located. So if we go to the left, one standard deviation to the left would be 22,000 less. So what's 57,000 minus 22,000? Not a trick question. 57 minus 22 is 8. 35. And Kate, 57 plus 22,000 is 79. So that means my salaries from 35,000 to 75,000 are one standard deviation from the mean. Those values represent 34%. This is where the previous chart will be helpful when you're making your own chart. Every single one is 34%, one standard deviation left, one standard deviation right. So then I need to go another standard deviation. So going again, continuing to add or subtract, you'll always do 3 standard deviations. So 35,000 minus 22,000 is 13,000. 79,000 plus 22,000 is 101,000. That number is 13.5 from the previous page, 13.5. And then one more time. This one's going to be negative. What's 13 minus 22? Minus 22.
Negative 9,000.
Negative 9,000. And then 101 plus 22 would be 123,000. And that percentage is 2.35 and then just 0.15 left. 2.35.15. So the reason you're organizing this information is because we need to answer a couple of questions about it. So once you have the salaries labeled, the percentages labeled, then you can start to answer some things. And some of them, you might have like 10 questions based off of one chart. So the question says, within what range do 95% of the lieutenant governor's salaries fall? So if you look at the chart, starting in the center, adding those percentages, 95%, what range would that be, Sarah?
That's second deviation.
That's the second deviation, standard deviation. So what range would that be? What does it start at? What does it go up to?
13,200.
So 13,000 to 101,000. 95% of the governors would have a salary that was in between those values. And that's just adding the percentages together. The second question, about what percent of the lieutenant governors have an average salary of 35,000 to 79,000? So now you're looking at the ranges. What percent of that falls within those two numbers? Virginia? So she said 68. So right here's 35,000. Here's 79,000. So 34% left, 34% right makes 68%. Questions? So if you go down below to the last question, the diagram's already shown for you. Pretty sure it's already shown. Okay, mine's cut off, but your diagram should be shown below, and it's already labeled for you. So see if you can put the percentages in the chart. So 34%, 13.5%, and then answer the 3 questions. So you're applying the percentages, the numbers down below are already listed.
Oh, that was my elbow. Sorry, I'm just kidding.
Please finish up that last question, and then the homework is just the front of this worksheet. Again, use the information of the bell curve that's drawn for you.
Jane, do you want to test that?
No, you can keep them for now.
Wait, front side, that's okay.
They're both copied on there for you.
Oh, right.
See you, house. Have a good day.
Have a great day.
You too.
Thanks.